I would like to be able to understand why the laws of physics look the way they do. But as in terms of why the universe exists, I think that will probably just turn out to be an ill-formed question. I think that there's no such thing as the reason why the universe exists.
Welcome to Closer to Truth. I'm speaking with physicist and philosopher of physics, Sean Carroll, about his superb, valuable new book, Quanta and Fields, the second in Sean's acclaimed series, The Biggest Ideas in the Universe. It is the clearest introduction to quantum mechanics and related topics with the real math that is both comprehensive and accessible, which sounds like an oxymoron, but for Sean, it is not. Sean, good to see you again.
Robert, thanks very much for having me on. Always good to be here.
I love the book. It's what I've been looking for. I learned a lot. I need to learn more. But before we dive in, let's start with one of the possible implications of quantum theories, the many worlds interpretation, which we're going to talk about later in depth. But just briefly, because I read in the April 9th issue of New Scientist magazine, an article that headlines, "The multiverse could be much, much bigger than we ever imagined." And it considers innumerable subsystems of the world. You're quoted quite extensively, quite well, as taking this seriously. Why do you take that seriously?
Well, many worlds in general is a wonderful and compelling idea. I take it seriously because it's the most straightforward implication of the equations of quantum mechanics, in particular, the Schrödinger equation of quantum mechanics. Every other version of the foundations of quantum mechanics either changes the Schrödinger equation sometimes or adds new elements to it or something like that. Let me just be super duper clear for the listeners. I wrote a whole book about the many worlds interpretation of quantum mechanics and why it's good. In these books, in The Biggest Ideas, I don't talk about it that much. I'm much more focused on what we truly believe that we understand, not speculations that go beyond our current knowledge.
Right. No, that's clear from the book. But in the article, it talks about the idea of subsystems where any two aspects of the world, what I'm doing here on Earth and something that just happened in an Alpha Centauri, could be looked upon as a subsystem. Does that in any way expand the traditional Hugh Everett traditional interpretation of many worlds? Because that was the implication of the article.
Well, I think that it depends on what you mean by the interpretation. At its very most basic level, Everett is just saying there is something called the quantum state, which everyone agrees there is, the vector in Hilbert space, if you want to be technical about it, but the wave function of the universe, if you want to be poetic, and it always obeys the Schrödinger equation. That's it. That's the entirety of the interpretation. Everything else is commentary, including the fact that there are many worlds. And so there's a long-running debate among people who care about the Everett interpretation about what counts as a world. Where do we draw the dividing line between the different worlds? And so we're thinking about the possibility that you can be pretty comprehensive in dividing it up into a very large number of worlds. But the important thing is this doesn't change the Everett interpretation at all. It's only a question of, is this a more convenient way of thinking about it for we limited human beings?
Okay, well, there'll be more to come of many worlds. We'll get into it later in more depth, but it is certainly fascinating. We'll conduct our discussion in three parts. First, I want to go through each chapter of the book just to get an overall high-level sense of Quanta and Fields. Then I'm going to pick out several what I think are interesting issues from the book that we can discuss in some depth. And then finally, we'll have sort of some speculations about the implications of quantum mechanics and the nature of reality, all good, close to the truth subjects. But first, let me give a serious, though quick bio. Sean Carroll is the Homewood Professor of Natural Philosophy at Johns Hopkins University, a joint appointment between physics and philosophy. Sean's research has focused on cosmology, field theory, and gravitation, shifting to more foundational questions in quantum mechanics. In addition to the Biggest Ideas in the Universe series, he is the author of many best-selling books, including Something Deeply Hidden, The Big Picture, and From Eternity to Now. He is the host of the popular Mindscape podcast. Sean, lots to cover. Again, we're going to use the chapters of your book as a framework. So let's look for a high-level discussion in the overview, which is just to give some fundamentals. Just define quanta and fields by contrasting it with what we know from classical physics.
Yeah, it's a 3-volume series that we're in the middle of here. Volume 1 was space, time, and motion, classical physics. Volume 2 is quantum physics, but that has to include modern ways of thinking about quantum physics, which are based on quantum field theory. So a lot of the book is about quantum field theory.
Mm-hmm. Okay, and what is the major contrast between quanta and field? So define each of those terms briefly.
The idea of quanta comes from the fact that we actually, in the formulation of the theory, quantum mechanics, we don't think about a lattice or discreteness or pixels or anything like that. Everything is smooth and continuous. But when we observe it, the world appears to us in lumps, in particles, which we call quanta. And fields are the fact that the thing that we quantize to get our best picture of nature are fields that fill all of space rather than particles that have a definite location.
Okay, and that's a very significant point, a major part of the book, and we'll get into that. Okay, chapter 1 is on the wave function. Giving the position and momentum of every constituent specifies a classical system, and giving the wave function specifies the quantum state of a system.
Yeah, this was a dramatic change because Isaac Newton, we thought, had laid down the law for classical mechanics. What the world is some things with positions and momenta. Quantum mechanics comes along and says, no, there's something called the wave function, and we can figure out how to predict things as best we can from it, but it's an utterly different thing than Newton would have thought.
And for the wave function, that is not designed as a representation of reality. It's it means it is reality. It's a big difference in science.
We don't agree. No one knows. I think that reality is completely represented by the wave function. In other words, reality is reality, but the wave function is in a mathematical one-to-one correspondence with reality. Others think that it's only part of reality or it has nothing to do with reality. So that's where opinions differ.
Okay, sounds like a big difference. So you bring up the Schrodinger equation. Very briefly, describe it.
The Schrodinger equation is what replaces, in quantum mechanics, F equals ma from classical mechanics, the equation of motion, Newton's second law. It's the thing that says, okay, I've told you what the world is. Newton would have said positions and momenta. Quantum mechanics says it's a wave function. Now tell me how it evolves, how it changes over time. That's what the Schrodinger equation does.
Great. And one other point from this chapter, which comes out as important, is when you use the Hamiltonian, which you discuss in your first book, in quantum mechanics, that becomes an operator. And so give us just some sense of what an operator is in terms of a mathematical function that characterizes quantum mechanics versus classical mechanics.
Yeah, so I was happy enough in book 1 to talk about something called the Hamiltonian, which is a fancy way of saying the energy of a system as a function of the positions and momenta of everything. So you have some complicated arrangement of stuff, and the Hamiltonian is one number. It's the energy of that particular arrangement of stuff. In quantum mechanics, the Hamiltonian, like many other things, is not a number. It's an operator, which means I start with a wave function with some quantum mechanical state, and the Hamiltonian operates on that to give me a different wave function. And then I can do things with it, like plug it into the Schrodinger equation.
Good. So that's a very significant difference. Okay, chapter 2 is on measurement. Let's start very quickly is what is the measurement problem?
Well, this is the big thing for the foundations of quantum mechanics, right? Because if all that had happened when we invented quantum mechanics was to replace positions and momenta with wave functions, that would be slightly annoying, but we would deal with it. Waves are things that physicists know how to deal with very, very well. The problem is that when you look at a quantum system, it doesn't look like a wave function. It looks like particles or something like that. So the measurement problem is, what do you mean when you say look at a system? What exactly happens? What counts as a measurement? What can make it happen? What kind of agents can make it happen? Why are measurements important at all?
Yeah, and many people extrapolate that significantly to say there has to be a conscious observer, and this has great philosophical implications about the nature of reality or the nature of consciousness, which I don't think we agree with.
Well, I don't agree with it. I'm not going to put words in anyone else's
Well, I said
mind,
we,
but
meaning you and I.
yeah, right. So, we don't know what the answer to this measurement problem is, but it's not that we have no good ideas. We have lots of good ideas. And what we teach our students is not very good, is not very sensible, is not very coherent. It's just that when you measure something, the wave function suddenly changes, it collapses, but you're not allowed to ask what it means to do a measurement, what counts as a measurement. So it's good enough. That sort of
Hmm.
half-baked version of quantum mechanics is good enough to win many, many Nobel Prizes,
Hmm.
but it's not quite precise and clear enough to be a well-formulated theory of reality.
In this chapter, just give some sense of what Hilbert space is and how that compares with regular space and why that's important in quantum mechanics.
Yeah, it's too bad that the word space is used here, and I blame the mathematicians for this.
Okay.
They consider any set with interesting structures on it to be called a space,
Hmm.
right? So the space of all possible blah blah blah. Very different than the three-dimensional space that you and I live in. So Hilbert space is the mathematical space where all of the wave functions live. Every possible quantum state of the universe is an element of Hilbert space. And John von Neumann, the famous physicist and mathematician, showed that mathematically, Hilbert space is a vector space. That means that quantum states are vectors. You can add them together. They have a direction. They have a magnitude. They don't have a direction in physical space in the three-dimensional world. They
Hmm.
have a direction in this gigantically dimensioned thing called Hilbert space.
Chapter 3, Entanglement. A very interesting point you make is that when we think classically, we think particles. And when we think in quantum, we first think of the quantum state, then particles.
Yeah, and importantly, when you have more than one particle in classical mechanics, it's not a big deal. You just add more particles. You describe each particle individually. The classical world is separable. You can treat each part of it all by itself and then add in what its interactions are with the rest of the world. Entanglement in quantum mechanics says the quantum world is not like that. There are not separate quantum states for different parts of the universe. There is only one wave function for the whole universe all at once. And that has important experimental implications. You can measure one part of the universe, and that tells you something about the possible measurement outcomes somewhere else.
Chapter 4 is on fields, a very important part of the book because quantum field theory, as you state, is the single best way to describe the universe at its deepest known level. So quantum field theory really becomes the foundation out of which quantum mechanics and particles emerge.
Yeah, and I want to emphasize, there's 12 chapters in the book, and only 3 of them are about quantum mechanics by itself. We move very quickly
Yeah.
onto fields because it's such a rich, amazingly deep subject. And so in this chapter, chapter 4, we just make our lives very, very simple. We say, what if there was just one field in the universe and it didn't interact with anything else? It's all by itself. And what we show is that when you apply the rules of quantum mechanics to that situation, that field acts like a collection of particles, or more specifically, because quantum mechanics lets us consider superpositions of different things, like Schrodinger's cat being partly awake and partly asleep, you could have a quantum field representing 0 particles and also 1 particle and also 2 particles, etc., all the way up all at once.
And significantly, then particles are really the quantized excitation of fields as opposed to entities in themselves. This is, I think, one of the most fundamental points.
Absolutely. It surely is. As I say in the book, if you were a physicist working at the end of the 1800s, you would have been forgiven for thinking we were almost done with physics. Classical mechanics seemed pretty good. And you could divide the world into particles and fields. Particles like electrons or atoms, fields like the electromagnetic field, the gravitational field, and so on. And quantum field theory unifies all of that. It's all fields, But when you look at fields, when you measure them in precisely the right way, they appear to us as particles. So it's really only one thing going on deep down.
So the implication that particles are quantized excitation of fields answers a fundamental question. With all the number of electrons in the universe, or protons 10 to the 80th, or whatever the number is, how could they all be exactly the same? Because it just seems impossible. But when you think of them as not as entities that we have to explain why they're all the same, but they're all the product of a field, the answer becomes obvious.
You know, you're right. There are about 10 to the 80th electrons in the observable universe. You got the right number there. I'm very impressed. That was very nice. And you're also right that the reason why every electron is identical to every other electron is because fundamentally the world is not made of electrons or other particles. It's made of fields. And there's something called the electron field. And when you poke at it and make a little vibration, that shows up to us as an electron particle. But the underlying field has the same physical properties no matter when or where you are in the universe. So every electron looks identical to us.
And not only look, but they actually are.
They actually are. And quantum mechanics has a lot to say about that. Yes.
Okay, chapter 5, interactions.
Well, of course, this is where things truly become exciting and mind-bending, because in the previous chapter, we showed that if you had just one field all by itself, not interacting with anything, it would look like particles, but there's nothing to look at it, right? In order to look at it, you need other fields interacting with it. And that's where we get to talk about Feynman diagrams. Feynman was the one who really showed us how to think about interacting quantum fields. Two electrons come close together. They interact by tossing back and forth some photons or some other particles. They scatter off to go elsewhere. Sometimes the answer is infinity, which worries you. That'll be another chapter. But the point is, there's a recipe for going from some specific kind of interactions that you specify dynamically to all these little pictures of what happens, which gives you a way of calculating your quantum mechanical probabilities.
On a simple look, Feynman diagrams just seem almost Lego simplistic. Why are they so powerful when they look so simple?
Well, that's a great question. And, you know, one of the motivations behind writing this book is to move beyond the idea that Feynman diagrams are just cartoons, right? Because in a book like this, my grand ambition is to show people the equations, to unveil the specific quantitative relationships beneath the metaphors and analogies that we usually get. So in a traditional popular science treatment, including ones that I've given myself, you will draw a Feynman diagram and you'll say this represents this interaction, blah, blah, blah. But you're left a little unsatisfied because, you know, why did I have to draw that diagram? So here in this book, we explain that every diagram is a number. Diagrams can be used to calculate quantum mechanical amplitudes, basically to calculate the wave function for this particular process. And from that, we can get the probability of observing that process. So they're not just cute little pictures of what happens. They're fiercely quantitative ways of measuring and characterizing the probability that something happens.
Chapter 6, effective field theory.
This is my favorite chapter. I don't know if it's going to be anybody else's favorite chapter, but, you know, we alluded to the fact that these Feynman diagrams, which are supposed to help us calculate things, can easily lead to trouble because you calculate a number and the number is infinity. And this seems bad. And so Feynman and Schwinger and Tomonaga won the Nobel Prize for wrestling with this, showing us that we could get away with it. But it always seemed a little unsatisfying, the process called renormalization. Feynman himself was not happy with renormalization throughout his life.
It just sounds like a fudge factor.
It does sound like that, but basically it was all figured out by Ken Wilson in the 60s and 70s. And somehow the world doesn't know about this, and the world should know about this. What Wilson said is that the reason why Feynman diagrams give you infinity is because you're including particles with infinitely big energies. And you don't know what's going on when particles have infinitely big energies. Maybe space-time doesn't exist or something like that. So he showed us how to just remove those unwanted, ill understood parts from our Feynman diagrams. And we are left with what is called an effective field theory, because they are very, very effective.
Chapter 7, which is one of my favorite chapters, which you call scale, and you introduce the idea of scale by saying the number of nucleons, basic neutrons and protons, in various orders of magnitude. Human DNA or bacterium would have 10 to the 12th. A human being would have 10 to the 28th. The Earth would have 10 to the 51. The sun would have 10 to the 57. So that's a million times more. Exponents of 6 is a million. And so the Earth is roughly a millionth the size of the sun, which is right. Milky Way galaxy, 10 to the 70th. I think that looks like 10 trillion suns, which is more than the number of stars in the galaxy, but there's a lot of gas and other stuff. So that's order of magnitude, right? And then the whole observable universe, 10 to the 80th, which is 10 billion galaxies seems actually low, because I think that now 10 trillion, so maybe it should be 10 to the 82nd. But you see this beautiful hierarchy, and that to me, that's the best, simplest way to get a sense of the structure of reality. I mean, it's literally breathtaking.
Yeah, this chapter is kind of a reward. It's a little respite. You've just done the last couple chapters were pretty heavy going,
That's the way
dealing
I
with
felt.
Feynman.
Right, very good.
It's a lot, and so we want to put it together and as you say, reflect on the beautiful structure that comes out of this, because this talk about quantum mechanics and field theory, sometimes it's said this describes the world of the very small. But actually describes the whole world, including the very big. It's just you don't need it to describe most features of galaxies or stars. You need it when you get down to subatomic particles, but they all fit in to the quantum field theory framework.
Yeah. An interesting point in this chapter, which is a great way to understand how the world works, is the fact that we know that protons and neutrons are made up of quarks, 3 quarks, different colors or characteristic strangeness, and they come together in different ways, and we think that's what composes it, and they're held together with the boson, the force of gluons. But the point that you make, which is the critical point, is that if you took out all the quarks and only had the equivalent masses of the force, which is the gluons, the total mass wouldn't get that much less. I mean, that's an astounding idea.
Yeah, this is why it's necessary and useful to think about quantum field theory, because sometimes when you have an electron going through your bubble chamber or whatever, you don't need to think about the details of quantum field theory. You can just think of it as a particle moving in a certain trajectory. But inside a proton or a neutron, the world is very different from the world of our intuition of particles and so forth. So we're told, once again, in a pop science level, that a proton has 3 quarks inside. But the mass of the proton is much bigger than the sum of the masses of those quarks. Mm-hmm. And also, another thing that I go through in the book is there's something called the Compton wavelength of a particle, which is roughly, the size you can squeeze its wave function down to. And the Compton wavelength of a quark is much bigger than the size of the proton that it squeezed into. Mm-hmm. So what is going on here? And the answer is that you should read the book, because it's all about quantum field theory and it all does make sense.
Okay, so now I'm going to go quickly through some of the later chapters. 8 is symmetry.
Symmetry is very important. Whenever you hear things like the standard model is an SU3 cross SU2 cross U1 gauge theory, mm-hmm. What do all of those symbols mean? What do all those words mean? It's all about symmetry and group theory, and that's where I explain this in the book.
Chapter 9 is gauge theory, which is a particular kind of field theory.
That's right. So the previous chapter was about the mathematics of symmetry. Gauge theories are putting that mathematics to work in quantum field theory. It is the existence of certain kinds of symmetries, gauge symmetries, that give rise to the forces of nature. The reason why there are forces is because of a symmetry in the underlying quantum field theory.
And this transformation can be done at any point in space-time.
That's what the word gauge means in gauge symmetry. It means that I have Red, green, and blue quarks, for example, that's a three-dimensional space, and I can rotate it. That's a symmetry, an SU3 symmetry. But I can rotate it separately at every point in space-time, and that means I need a new field to be able to connect them. That field turns out to be the gluon, which holds particles together.
One of the points you made I had a little difficulty with is from gauge theory. You can derive the idea that the force carrying particles are naturally massless, like the like the photon, etc. I didn't
Yeah.
quite get that. How you so quickly get to that conclusion, which is obviously important.
Yeah, it is. So we talk about in earlier chapters what it looks like when a field has a mass. It all comes down to the dynamics of the field. It's a way for the field to interact with itself so that its particles move slower than the speed of light and have what we would call a mass. The more force you put on them, the more they accelerate, like F equals ma in Newton's laws. Now, gauge symmetries come along, and there's a symmetry there which very, very tightly restricts the possible terms you can write down in the equations of motion for these particles. And it turns out that the particular kind of interaction you need to give those particles a mass is forbidden by the symmetry.
Mm.
It would break the symmetry if you just naively wrote it down. Well, you can write it down. People did. And they're like, now it's not gauge invariant anymore. So that symmetry not only gives rise to a new force, but it implies that the particles carrying that force should be massless, whether they're photons or gravitons or gluons.
Mm. Chapter 10, phases.
This is a big one because I just told you that gauge symmetries imply that force-carrying particles are massless. But in nature, we have things called the W and Z bosons, which are force-carrying particles which are not massless. What's going on with that? And the answer is that gauge theories can appear in different phases, very analogous to like the phases of water being ice or liquid or vapor. There's different ways to apparently break the symmetry, not really break it, but hide it. And that gives masses to the W and Z bosons, not to mention particles like the electron and the quarks.
I'm very familiar, most people are, with the standard model of particle physics. Steven Weinberg particularly personifies that. You introduced the idea or explained the idea of core theory as well. So how does the standard model articulate with core theory?
I borrowed that term from Frank Wilczek, who introduced it, and it's basically a way of reminding you that gravity is less of a bad fit than you might think. We have this thing we say, we don't understand quantum gravity, et cetera, et cetera. What would be more accurate to say is that we don't have a full, complete, final theory of quantum gravity. We don't have a theory of quantum gravity that includes black holes or the Big Bang or things like that. But as long as gravity is relatively weak, like all of the solar system, including the sun, the earth, et cetera, we're nowhere near making a black hole. Gravity is pretty weak. Under those circumstances, we understand quantum gravity fine. So the core theory is just the standard model of particle physics plus gravity in that weak field regime.
Okay, so the standard model is a subset of core theory with the asterisk that this applies to low levels of gravity.
Yeah, that's exactly right.
Okay, good. Chapter 11 on matter, bringing things together.
Well, matter is could mean almost anything, but what I took it to mean, what I wanted to explain was why when you have certain kinds of fields, bosons, like the Higgs boson or the photon or whatever, they can pile on top of each other and give you a classical force field. Whereas other kinds of particles, fermions, like electrons and neutrinos and quarks, they take up space. They make up matter. The table in front of you or whatever has a certain solidity, a certain density, because some particles take up space. I explain why in this chapter.
Okay, and that's why my hand don't pass. Are not. I can't interdigitate. I can't put my hand through a table, and that's because the difference between the matter and the forces.
The reason why you can punch somebody effectively is ultimately because electrons do not want to be in the same quantum state. Yes.
Okay, chapter 12, atoms.
Yeah, so for the final chapter, we put it all together and we answer the question, if there's all these particles out there, Higgs bosons and top quarks and whatever, why are you and I made of so few particles? Electrons, protons, neutrons, a couple of force carrying particles. So we talk about the dynamics of these particles and how they decay into each other. What are the stable final particles? Why do neutrons become stable inside a nucleus but not outside a nucleus? How does it all fit together to make up the periodic table of the elements?
And the big question of baryon asymmetry, where in the early universe, I think you say there was 10 billion anti-baryon particles versus 10 billion plus one baryon, and therefore all the 10 billion canceled out, but the one left over out of 10 billion uh, becomes the entire universe.
That's exactly right. And we don't know why. And I'm going to be very honest. I'm not going to tell you why in this book because I'm sticking to things that we know. That's one we don't know the answer to.
Yeah, and that you said it before, but it's an important point about the book. We have these very speculative ideas. You've dealt with it in other books, but this book is really the depth of the understanding of what we do know and what we're sure of, and how that works. Okay, let's go into our second part, which is just taking some of the issues that are just fascinating and dealing with it. And let's start with wave particle duality. And in particular, the celebrated double slit experiment. And why is that so important?
Yeah, wave particle duality is honestly overrated. I think Edward Witten once said, the battle is over, the waves have won. The world is clearly made of waves. But it appears like particles under certain circumstances. That's the magic of quantum measurement. So what the world is very wave, very field-like. But under the right circumstances, when you measure something, it looks like a particle. The double slit experiment is a famous example of that, where you say a single electron can pass through two slits and interfere with itself. If you really just accept that electrons are not particles, they're described by wave functions, that's the least surprising thing in the world. Waves can interfere with each other.
Right. And how deeply do we understand that? There's some would speculate that the double split experiment is evidence for the many world interpretation. You wouldn't go that far, would you?
I would not go that far. I think, again, all you need to believe in is the reality of wave functions. Now, some people don't. Some people think that wave functions are just ways to calculate experimental outcomes, and we should not attribute reality to them. And I think that those people have a very difficult time in explaining things like the double slit experiment. They can do it, but they kind of have to bend over backwards to do it. So if you just trust the equations, if you just believe what is sitting right in front of your face, here's a wave function, here's the equation it obeys, everything I think makes perfect sense. I don't think the double slit is especially mysterious.
The Heisenberg uncertainty principle is almost a household word and is used in many forms. One of the highlights of the book to me was understanding it in its deeper meaning and to really appreciate why it is the case. So give me a brief sense of that.
Yeah, it's, again, not a postulate of quantum mechanics. It's something that pops out of the formalism of quantum mechanics. But it's fascinating to me because Isaac Newton, in his formulation of classical mechanics, says very clearly, you need to tell me the position of something and its momentum, and then I can predict where it will go. The state of something is its position and its momentum. Quantum mechanics comes along and says my wave function is psi of x. That is to say, for every possible position of the particle, I can attach a wave function number, and then I would square that to get the probability of observing it. So where did P go? What happened to momentum? P is the letter that we use for momentum. How can you possibly capture everything there is about the system in terms of just the wave function as a function of position? So I explained the answer to that. We know what the answer is. And the answer is, remember, quantum states are vectors in Hilbert space. And basically, when you have a vector, if you just do have x, y, and z, then you have components of the vector. You've chosen a basis. You're going to tell me what the vector is by giving you the components. In quantum mechanics, the relationship between position and momentum is changing bases, changing the fundamental axes along which you measure your vector. And then if you believe that, if position is one kind of basis, momentum is a different kind of basis, the uncertainty principle is automatically true. It's almost trivial. In fact, there are physicists out there who will say, oh, it's just obvious. You shouldn't be worried about it. Because if you've rotated your vectors, you can't be completely 100% in a direction in one basis and also complete 100% along an axis in the different bases because they're rotated with respect to each other. So that's an example. It's a great example where a little bit of math, I think, makes everything much, much clearer.
It pops out, as you said. It's a forced realization as opposed to a brilliant new idea.
Yeah, I mean, it was a brilliant new idea when Heisenberg came up with it, but honestly, we understand quantum mechanics better now than we did in those early days. So it does, once you understand what quantum mechanics is trying to tell you, the uncertainty principle just comes along for the ride.
You make the statement that entanglement helps us understand measurement. That was, to me, one of the most interesting statements in the book. These are two of the most important aspects of quantum mechanics, obviously, and you link them together. How does that happen?
Yeah, I actually struggled while writing the book with the fact that we don't agree on the basic language with which to talk about quantum mechanics. We don't agree on whether wave functions are real or not. And I decided that, rather than on every page saying, well, if you think this, you would say this thing, and then this, that would just drag it down. So I said, we're going to talk as if wave functions are real. I mean, I happen to think that they are. I happen to think that is the right way to think about reality, but it certainly provides a much easier way of talking about what happens in quantum mechanics. And if you accept that, then we have an answer to the question, what do you mean by doing a measurement? And the answer is a measurement happens when a quantum mechanical system that, again, it can be in a superposition, like spin up and spin down at some fraction of each. All by itself, that's fine. A measurement is when that system becomes entangled with the rest of the world. And that's when the two parts of the superposition are no longer sort of living by themselves. They're now related to everything else in the universe. That's what we call a measurement.
Okay, you also make the point we talked about a little bit earlier of the wave function of the universe that, and the basic idea, I think, is that no matter how you define your system, whether it's, as you said, two particles or the entire universe, there's still only one wave function of that system. So give me some color around that.
Yeah, this is one of the things that is very, very difficult for people to wrap their brains around because we look at the world around us, we see many separate objects. That just seems to be pretty obvious. And quantum mechanics, to put it in closer to truth language, is more of a monist theory. It says there's really only one thing, the wave function of the entire universe. And so people struggle to understand it. But what I would advocate is just accepting that, accept that there is only one thing, and ask the other way. Ask, why does this one thing, the wave function of the universe, appear to us as many things? That's the surprising thing. Why does it look like apparently the world is made of many separate things? And that's an answerable question. It comes down, again, to measurement, what we call decoherence, which is when these quantum systems that are in a superposition become entangled with the rest of the world. And it all does ultimately make sense, even if it doesn't come close to our everyday intuitions.
What is the hierarchy problem?
Well, we mentioned before the core theory, right? The standard model of particle physics plus gravity. It's a theory that fits essentially all of the data that we have from laboratory experiments here on Earth. It doesn't fit some things in outer space, which is why we need dark matter and dark energy, et cetera. But here on Earth, it does a very good job. The problem is, even though it fits the data, there are parameters, coupling constants, numbers inside the core theory that are very, very surprising, that are not at all what we would expect if those numbers were just chosen randomly. The hierarchy problem refers to the fact that there are two parameters. One is the Planck scale, the scale at which gravity becomes important, okay, 10 to the 18 billion electron volts. And then there is the mass of the Higgs boson, which tells us the electroweak scale, the scale for particle physics, if you like. And that's at about 100 billion electron volts. But If you read chapter 6 on effective field theory, you will learn that particle physicists see no reason why these two scales should be so different from each other. You would naturally expect them to be very similar to each
Mhm.
other, and they're different by a factor of 10 to the 16, which is just a little crazy. That's the hierarchy problem. We still don't know the answer to it.
And also, how about the relationship between the powers of the forces between the electromagnetic and the gravitational power of forces? There's a huge difference. Once again, if you're just imagining a universe or a world, you wouldn't think there'd be such a vast difference in scale.
Yeah, this is where it becomes very, very tricky because you have to ask, how do you measure these things? Like, after all, the electromagnetic force between two neutrons is zero, but the electromagnetic force between two protons is considerable. Gravity is different because everything is affected by gravity.
Mhm.
So the difference in the strength of the forces is actually not something that physicists spend a lot of time dwelling on. That's harder to sort of know what your expectations should have been. There's something called the weak gravity conjecture that conjectures that there are good reasons why gravity has to be the weakest force. But honestly, that's beyond the scope of the book here. So we're trying to stick to things in this book that everyone will still agree on 500 years from now.
Good. Well, that's a challenge, but I think that's a very admirable one, and very clear in terms of the purpose of the book. In that area of hierarchy, and we have the cosmological constant, which, as you point out very strongly, is the vacuum energy of empty space, quote unquote. But the difference between the calculated theoretical value and the observational value is, as you say, 10 to the minus 122. So that's 10 to the minus 122 zeros, which is the largest mismatch in all of physics and all of reality in terms of the relationship between theory and experimental observation. And so, what does that tell us?
Well, we're not sure what it tells us, to be perfectly honest. Again, this is an open problem. I think that the contribution of a book like Quanta and Fields is that the reader can truly understand the problem in a
Okay.
way that it's harder to do otherwise. Because once you understand what quantum field theory is, and once you understand how effective field theory works, now you can follow the argument that says something like the vacuum energy should be a certain number,
Hmm.
because it's certainly not a clear, crisp prediction, right? We actually don't know what the vacuum energy should be. We have rough back of the envelope expectations for what it should be. And if it had been off by 10 to the 2 or 10 to the 3, then we would have dealt with that. We would have rolled with that and said, okay, that's how the cookie crumbles. But when it's off by 10 to the 122, then we go, I bet there's a reason why. I bet there's an explanation. I bet this is not just luck, right? And again, I'm not going to tell you what the answer is in this book, but I'm going to help you appreciate why physicists think it's a real problem.
And the quantum field theory is the foundation of what creates the problem, in a sense.
100%. Quantum field theory is super, super, super successful at fitting the data once you put in these incredibly finely tuned, seemingly unnatural parameters for certain parts of the laws of physics. So it's kind of a weird problem. It's not the usual thing in science where we have a theory, it makes a prediction, and then the experiment says, no, that's not it. This is not a place where we have a prediction. We have a feeling, we have vibes, right? And so the question of how seriously we should take that is a very good one.
Okay, now we go on to part three, which is pure speculation. And so we want to emphasize that the book gives everyone the capacity to understand the what is real and what is known today, and can therefore look at speculative ideas from from the unified foundation that we have of particularly quantum field theory. So what comes now is pure speculation, Sean.
Good.
Not, we're just going to just ask your feelings, and won't hold you to them if you want to change it the next time we talk. So the first one, I've got to go back to the many worlds interpretation, which you have forcefully and very strongly articulated and advocate. And I don't want to. Obviously, there are differences. There's pilot wave, Bohmian mechanics, all sorts of different explanations. But I don't want to put that aside. I want to say, okay, if the many worlds interpretation is real, if that is the way reality is, how does it work? I mean, there are 10 to the 80th numbers of particles, maybe 10 to the 90th photons. Each one can be analyzed in terms of the Planck time of each one and different relationship. How do you deal with the way to even think about the number of worlds? Is it 10 to the 80th or 90th factorial in some sense per Planck time? I mean, I just want to get a sense of the order of magnitude of how you think about many worlds.
Yeah, I mean, the real answer there is I don't think about all those other worlds that much. Again, the worlds are a prediction of the theory. They're not what the theory is fundamentally about. The theory says the world, the total world, the whole universe, what we can see and what we can't, is described by a quantum mechanical wave function. And that wave function obeys the Schrodinger equation. That's the theory. And we're trying to work out the consequences of that theory. One of the consequences is when you do a quantum mechanical measurement, and again, measurement can be defined independently of people or consciousness. Right. It's just about becoming entangled with the rest of the world. The world branches into multiple, somewhat classical looking parts. The different parts look individually almost classical, but they're separate from each other because in one, the spin was up and the other the spin was down.
I appreciate and understand all of that. I'm just trying to get a sense of the order of magnitude of the numbers. If we take, a period of time, 1 second, which you can divide into the Planck time, how many different total worlds emerge from that, given the number of the particles in the observable universe?
Right. And I'm trying to convince you to not worry about that.
That
is the wrong question to worry about. Because let me say two things. Number one, we don't know. Is the answer, because in order to know that, you would have to know the dimensionality of Hilbert space of the fundamental theory of everything. And we don't know that right now.
Can you give me some boundaries? Can you give me?
I'm trying. It could be infinite, right? For many simple quantum mechanical systems, the best description is in terms of an infinite dimensional Hilbert space. And in that case, it would be strictly nonsensical to ask how many worlds are there. It's like saying how many points are there between 0 and 1. But what you can do is compare the number of points between 0 and 0.1 to the number of points between 0 and 1. You can give the relative amount of worlds with certain qualities, and that many worlds is able to do very, very well. But it's also possible that the magnitude of the dimensionality of Hilbert space is finite. Indeed, I think that quantum gravity suggests that it probably is finite, at least when you only consider our observable universe. But the number is very big. The dimensionality of Hilbert space for our observable universe is something like 10 to the power of 10 to the power of 120.
Okay.
So that's plenty of room for lots of worlds to happen. We're not going to run out of room anytime soon.
So that's a question of the phase space or the capacity, which is obviously 10 to the 10 to the 120 is enormous. But it doesn't say how many of those occur every period of time. Can you put a bound on that? No. If many worlds is correct, within a period of time, 1 second take, what is the lower bound and what is the upper bound? Is there any way you can do that?
No, I can't, because again, the theory doesn't talk about worlds. Worlds are things that human beings invent to talk about the wave function of the universe in a convenient way.
Okay.
Two people might decide to divide up the wave function of the universe differently. As long as they agree on what the wave function of the universe is, they're fine. So the question of what is the number of worlds is just like, what is the number of colors?
Okay, let's go on to fine tuning, which has been extant in physics. It's been extant in science, theology discussions. How do you view the fine tuning of the universe, particularly in light of quantum field theory?
Well, I think that the word fine tuning gets bounced around in at least two very, very different senses. Very often in the popular discourse, it has something to do with life, right? That the universe is finely tuned to allow for the existence of life.
Or
But
structure? Yeah, right.
but physicists will often use the word fine tuning in a way that has nothing to do with life, just to say that certain parameters, like the mass of the Higgs boson, for example, in our equations seem to be represented by adding up many different numbers. And the many different numbers are individually much bigger than the sum of them that you get for the
Mm-hmm.
Higgs boson.
Mm-hmm.
And that's not impossible because some of the numbers are positive and some of the numbers are negative, but somehow they cancel out to give you a much smaller number than you would expect. And that's fine tuning to a physicist. So I think that the fine tuning problems of physics are important clues when we're moving forward to try to understand the laws of physics better. Whether or not they have anything to do with life, I would not be competent to talk about.
And therefore, your feeling is that nobody is competent to talk about that in a fundamental sense.
Well, I'm all in favor of talking about it, but remaining humble that we don't know the definition of life, the conditions under which life started, the
Yeah,
total set of other possible laws of physics that would allow for life, or anything like that.
yeah, and when we talk about life, that's sort of the end result. I mean, we're talking about structure to begin with. Why is there any structure at all that seems to be fine tuned? That if various parameters would be off by some argument what it would be, you wouldn't be able to have any structure at all. Everything would collapse into a black hole, or would fly apart without structure. And why we have this so-called fine tuning. So the question is, from a quantum field theory point of view, is there any color that one can bring to that kind of question?
I don't think that quantum field theory really tells us that much specifically about why and where and how complex structures can evolve. It gives us the basic ingredients out of which those complex structures evolve. I will tell you that I have a feeling that a lot of people are too quick to say that if conditions were different, complex structures would not be able to evolve. Because guess what? We're very familiar with our conditions. And I don't think that I could hand most people the standard model of particle physics and they would successfully predict the periodic table of the elements, much less life and stars and things like that. So again, I just want to be humble about the question, if things were different, would we even be able to imagine life coming into existence?
I'm just not used to in our conversations humility from either one of us, so it's a little.
You gotta grow in your life, right? You
Okay,
gotta
well,
try out new things, put
I'll,
on new hats.
I'll take you as a role model and try to follow
All
in
right.
your humility attracting persona. Um, let's go to some basic, closer to truth kinds of questions. We've talked about it before. We like to ask the question, what exists, by which we mean, what are the fundamental, irreducible categories of reality, as few as possible that are irreducible?
Yeah, I mean, of course, I wish I knew the answer to that, but my best guess is a quantum wave function obeying the Schrodinger equation. I think that people get a little confused because they will then want to know, well, a wave function of what? When we're taught quantum mechanics, those of us who went through physics educations, you start with, a classical system. Here's a harmonic oscillator. Here's the electromagnetic field. And then you quantize it and you get a quantum theory of that. And I think that's a little bit misleading because nature doesn't work that way. Nature starts quantum mechanical from the beginning. And so my best guess as the fundamental thing that exists is some kind of quantum state obeying some kind of Schrodinger equation. Of course, what exact kind, we're still trying to figure out.
The other question we ask is, why is there something rather than nothing? Why anything at all? And I can put it in a different way, is there are there brute facts beyond which we cannot proceed even in principle? And if so, what is in that category of brute fact?
Yeah, I'm like 99% sure that there are brute facts, and the existence of the universe itself is one of them. but I don't know exactly which facts are brute facts and which ones are explicable. I would like to be able to understand why the laws of physics look the way they do. But as in terms of why the universe exists, I think that will probably just turn out to be an ill-formed question. I think that there's no such thing as the reason why the universe exists.
Okay, that's been great, Sean. I loved it. Again, I recommend the book for everyone who really wants to understand quantum mechanics and quantum field theory as the foundation for all these kind of fun questions. So now we have a couple of short questions, and these are designed for stream of consciousness. Just give me a very quick answer, whatever comes to your mind. So the first one is, what do you think the best theory is to integrate quantum mechanics and general relativity?
Space-time emerging from entanglement in the wave function.
Question two, roughly, how long do you think it'll be? How many years will it be to get a general consensus on a theory of everything, whether it's what you just said in terms of integrating quantum mechanics and general relativity or some other theory? I mean, do you think this will happen in our lifetimes?
I'll say between 50 and 100 years.
Okay. Here, question three. On a scale of 1 to 10, your confidence level that the many worlds interpretation of quantum mechanics is correct and real?
9.5.
Next, on a scale of 1 to 10, your confidence level that the standard model of cosmology, cosmic inflation, the Big Bang, while it will certainly be refined, but it will not be overthrown.
Well, I would say 9.9, but I do not include inflation in the standard model. That's a speculation.
Okay. Last one, on a scale of 1 to 10, your confidence level that the physical world is all there is, that there is no thing that is not physical.
9.99.
Okay, well, your humility may have increased since we first began speaking, but your opinion of the non-physical has not changed.
It has
So
not.
we can give you consistency as well as humility. Once again, I love the book. Everybody can learn a great deal from it. I liked how you actually concluded that to understand the particles we're made of, the forces that how we interact, is one of humanity's greatest achievements. And you have this very beautiful line at the end. We can all be a little proud of that. So I love that.
Thanks very much. I mean, technically, I concluded with an appendix where I talk about Fourier transforms, but you're being very nice to talk about the poetic side of the last chapter.
We want to give a little bit of the softer side.
Yeah, good.
Once again, Quanta and Fields, indeed the entire Sean's entire series, The Biggest Ideas in the Universe, has my highest recommendation. Viewers can watch Sean's 27 videos and 8 TV episodes on Closer to Truth, and over 1,500 videos on cosmology and physics, especially their meaning and implications, not all of which Sean would agree with, on the Closer to Truth website and Closer to Truth YouTube channel. Thanks, everyone, for watching. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.